Okay, so in this video, we're going to look at kind of a messed up looking graph with all these discontinuities all over the place. And we're going to try and write various limit statements that deal with a lot of the locations on the graph. So one of the things we have to do is write a limit statement for the end behavior of the graph. So let's start right here. Oh, that's not the color I want, red. So let's look at this. I'll just call this location A. So at A, we can write this limit statement. So section it off. And this is one that we've been doing all year long, especially last semester. So way over on the left side of the graph, so that would be what happens as x goes to negative infinity. We'll call this whole function here, it's describing the end behavior of the graph, we'll say of f of x. All right. So now this graph is f. So the limit as x goes to infinity, negative infinity of f of x. You can tell that the y values there, the f of x values, get close to 1. So, and not only is that limit statement, if all I did was give you this limit statement, then you could say there's a horizontal asymptote at y equals 1 on the left side of the graph. So that's what you can determine just by looking at that limit statement. Okay, so let's go back to the graph. We'll do this and the we'll just go like left to right across the graph here as we write limit statements. So another place where this graph gets messed up is here at -2, where it's got a removable discontinuity right there, and the function itself has a value way up here. So let's come up with some sort of statement for this. So we'll call this section right here, we'll call this region B. So for B, if we look at that part of the graph, we know that as I get close to 2 from the left side, the function is close to -1. It doesn't actually matter when I write a limit statement. I'm saying what happens is x gets close to -2 from the left side. Notice it says as x gets close to -2, not what happens at -2. So just close to -2, the f values are close to -1, right? And if I look at the other side, so if we say what happens as x goes to -2 from the right side, well, on that side, it also gets close to the y value of -1. But if I actually said, well, what happens at -2, right? What's the function's actual value at -2? Well, that's way up here at 2. So one other thing that you're allowed to do, if the limit on the left side is the same as the limit on the right side of a certain point, then you can condense this into just one statement that says limit as x goes to -2 of f of x equals -1. And that, when there's no sign here, unless it's an infinity or a negative infinity, when there's no sign there, that just means both sides. Okay. One piece of information that you can get from the limit statements that go with B, if all I did was I gave you this and this, then you can actually figure out a little bit about the picture. You can figure out that when you're getting close to -2 and you're coming at it from either side, the y value is close to -1. And at -2, the y value is actually 2. So then you can actually figure out that there's a removable discontinuity right there. Okay? So these pieces of information tell you removable discontinuity at x equals -2. It's called a removable even if this dot is filled in up here. The idea is that if I filled in that hole, that discontinuity, at least I'd have removed it, right? Then it's continuous there. Okay. Let's do the next thing. So that would be this region right here, C. And for C, here, I'll shrink these down so I can keep writing here. So C is when x is around -1. So limit as x goes to -1. If we look at what happens on the left side of -1, that's right here, and the function just shoots off to infinity on the left side of -1. And it does it on the right side as well. So we could do another statement that just looks like this. Everything's the same except there's a plus there. Or I could just erase that minus, and that means that it's going to, whoop, I shouldn't have written negative infinity, just going to infinity on both the left and the right sides, right? Positive, sorry. Okay, let's take a look at this region here. Right, so we'll call that D. So D is happening around 2. So the limit as x goes to 2. Now I can't just leave this region blank because it's doing different things on the opposite sides of 2. If it was doing the same thing, then I could just do, then I don't need to put the plus or minus. But over on the left side, it's going downwards. So on the left side of 2, the closer I get to 2, the more that function turns into negative infinity. And on the right side of 2, I'll write this here. On the right side of 2, 2 from the right, this function is going upwards instead. So that's going up to infinity. When they're different like this, you can actually write, I prefer to keep those separate because they tell you which way they're actually going. But if they are different, you are allowed to say, if you tried to combine them into just x goes to 2, you would say does not exist, since they're different. Okay. Let's look, so this part is D. Let's look right here at E. So in E, we've got the limit coming from the left side here around 3 is a y value of 1, right? So the limit as x goes to 3 from the left side of f of x, that's going to be 1. That's the value that we approach there. The limit on the right side of 3 coming at it from this side, we get close to 0. And notice I didn't actually care what happened at 3. If I cared about what happened at 3, then I'd ask, what's f of 3? And that also happens to be 0. Well, if you look at just these two pieces of information, and let's say you didn't have the picture, then you could determine some stuff from the picture. If this is 3 right here, this says when x gets close to 3 from the left, the y value equals 1. So as x gets close to 3 from the left side, the y value is close to 1. And as x gets close to 3 from the right side, the y value is 0. So then what you have is, no matter what, right? Let's kind of do it like this. This is a y value of 1, y value of 0. No matter what, you've got this hole here and then a jump. So you can definitely determine that that defines a jump discontinuity. And it doesn't even matter if that hole's filled in or not, right? Oop. It could look like this, and it would still be a jump discontinuity. It just so happens that since the value is also 0 there, then you can fill in that one hole. Okay, Let's look at the end here, f. So that's going to be the limit as x gets bigger and bigger and bigger. The value of the function also gets bigger and bigger and bigger. Okay, there's one last thing that we have to do. That's look at the behavior of the graph near x equals 0. So that's right here. And notice that everything's connected right there. So we'll call this G. So for G, this one was F. For G, we have, if we come at the function from the left side of 0, we get a value of 2. And we also get it if it were from the right side, and since it's both, we can just say as x goes to 0. And then if I actually cared about what happened at 0, I'd get 2 as well. And so when you have this information right here, right, if the limit at a location for x equals the actual function, then you're going to get a nice continuous function like that at that point. Another way of thinking about it, let's think about limit as x goes to 0 of f of x equals 2. Well, that means coming from the left, I get close to a y value of 2. Here, I'll just do it like this. A y value of 2. This is x equals 0. Coming at it from the right side, I also get that value of 2. And then when I actually plug in 0, I get 2. So that fills in the dot, and now everything is continuous. So this tells us that we have continuous, or continuity at x equals 0. Okay, I hope that helps some. All right.